Okay, so my name's Philip Cardiff. I'm an associate professor in University College Dublin in Ireland. And this training is on Solids4Foam. So I'll spend some time of it going through some slides, and then I'll spend a little bit of time in the terminal. I guess it's not really long enough that I expect you to follow along. It's more something maybe you can refer back to if you want to follow along in terms of like doing it yourself. I was repairing the battery for my laptop this week. So this is my wife's laptop. So far it's working okay, apart from the fact there's only one port on it. So hopefully my battery doesn't need to be charged. And I think you can hear online. I'll try keep an eye on the questions. Okay, they're from the last time. People are saying great talk. So yeah, just feel free, people in the room, you can interrupt if you have a question, and on online you can just ask. Okay, I'll just start with Solids4Foam. What, why, how? So what is it? Why am I developing it? And then how exactly is it being developed at a very high level? So in short, Solids4Foam is a OpenFOAM toolbox for computational solid dynamics and fluid-solid interaction. So it's all OpenFOAM code, and it's to do solid mechanics simulations and fluid-solid interaction simulations. That's what it is. So for example, a lot of my research, some of it is related to metal forming, some metal forming companies. So this is like a verification test case for large elastoplastic deformations with frictional contact, things like that. So this is a tutorial you can do. You can also do this one, which we're going to look at. So this is just dam break. It's just the standard interfoam dam break, except we just make the dam flexible, and then we run it. So we have a little elastic, like rubber dam, so the fluids hit it and it bounces around. So this is one of the tutorials in Solids4Foam that you can try. So Solids4Foam is not the only way to do FSI in OpenFOAM. So there are a variety of different ways with different relative merits. Why does Solids4Foam exist? So generally, many people, probably many of you here, have a desire to do FSI problems, so fluid-solid or fluid structure interaction problems. So this is one way to do that. I had the same desire. Also, people may want to do solid mechanics or FSI natively in OpenFOAM. So it's quite a lot of investment to learn how to use OpenFOAM, understand what an OpenFOAM case is, and run OpenFOAM. So then if you want to do an FSI, well, one approach is you can learn Phoenix or FEBio or one of the many open source finite element softwares out there. But then it's basically like learning the whole thing again, like a whole new wheel you have to learn. It may be better, but maybe since you already know what an OpenFOAM case is, if you could just do it in OpenFOAM, that will be convenient for some people. And also the idea of a modular approach. So some of the earlier FSI stuff, I released a solver it's in OpenFOAM under solid mechanics called ICO FSI non-lin elastic UL foam. So it's basically picking ICO foam with a particular type of solid formulation and just putting them in one OpenFOAM solver so you can run it. So then I wanted to change it from ICO foam to pimple foam. So then I'd have to make pimple FSI ICO blah, 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 blah. So that's a real pain in the ass for code duplication. Code duplication is not a good thing in coding. So you don't want to duplicate code. So this modular approach, you'll see how Solids4Foam doesn't follow the design of OpenFOAM from the solver perspective. It has a different solver design perspective to minimize code duplication. And then separately, research into finite volume methods for solid mechanics. This is more just of a personal interest of mine. It has some curious characteristics relative to finite element methods or other methods that may be beneficial in some situations. That's the why. How? So the idea is, if you can use OpenFOAM, then you can run an OpenFOAM case, you can run a Solids4Foam case. Things will be where you expect them to be. Boundary conditions and initial conditions will be in the 0 folder. Okay, I'm going to ignore that. Material properties will be in the constant folder. You can change the time step where you expect it to be changed, etc. One desire is that I can support the main forks of OpenFOAM. So by the main forks, essentially there's 3 at the moment. There's openfoam.com, produced by ESI and OpenCFD. There's openfoam.org by the OpenFOAM Foundation, CFD Direct. And then there's Foam Extend. They're like the 3 main public forks. There are other ones as well. Unfortunately, that is the case. and they have some distinction. So I try using compiler directive support so that it will compile with each of those. Should be easy to install. Many people develop code in their PhDs or whatever as part of their research. Not many people are aware that OpenFOAM has a coding style. There's a page, OpenFOAM C++ style convention. They tell you what your code should look like. So this is not whether it compiles or runs correctly. This is a style. This is what it should look like. This is whether there should be a space or not after a for all loop. You might think that's absurd, but if you know what the style is, then when you see code in the same style, you can read it instantly. It's just like learning to drink water or something or ride a bike. When you see code that's not in that style, it's much more difficult for your brain to figure out which loop corresponds, where does it close. So, okay, people say, I'll do it when it works. I want to meet this person who will change the code after it works. So, okay, single executable design. So Solids4Foam only has one solver. It's called Solids4Foam. If you open up Solids4Foam solver, it's essentially just a empty wrapper class. It just says create an object of type physics model, which is a class, and then tell that to solve its equations. So it doesn't know anything about the equations. It just says there is some class called physics, solve physics. That's it. So that physics can be a solid or a fluid solid interaction case, and that's specified in the case. So this is the distinction. We have one solver, and then essentially the real solvers are all in classes. So we have a solid model class, an FSI class, a fluid model class. So for example, we have essentially a piezo or pimple fluid, which is just take piezo foam, copy the code, and put it into a class. Now I said I hate code duplication, and this is the disadvantage of this approach. You have to copy and paste a fluid model into its own class structure, but the advantage means then I can just create that solver wherever I like, whenever I like, tell it to do what I want. It's not an executable, it's an accessible object. So that's a fluid, and the solids are the same. There's very many types of solid formulations, just as there are fluids, whether it's compressible or incompressible in fluids, but it's the same idea in solids. You can have small strain or large strain, and there's a variety of formulations and etc. and solution methodologies. In fluid models, a key thing for accuracy is determining what the stress in the fluid is, and that comes from the turbulence model. The equivalent in a solid comes from what's known as the constitutive model or the mechanical model. So whether it's an elastic material or elastoplastic, viscoelastic, poroelastic, some other plastic type of approach. So there's a variety of different linear elastic models, and there's also even a wrapper for Abacus, Fortran, subroutines as well. For FSI, there are two main approaches to FSI in the literature. There's what's known as partition methods and monolithic methods. So partition methods solve the solid, then solve the fluid, and then you may iterate. And you pass forces from the fluid to the solid to move it, and you pass the motion of the solid back to the fluid to update the mesh, and you iterate, or you don't iterate, depending on it. So that's called partition. That's nice because you can have a black box fluid, black box solid. They don't need to know about each other. There's also monolithic, which is you discretize the whole thing as one big piece of mushy fluid solid, which is not implemented, but that's on my to-do list for a long time. I just need to find someone to pay me and researchers to look at it for 5 years. These slides installing OpenFOAM, I'm going to skip over these a little bit because we're tight for time. You can find, if you want more, there's you'll find similar presentations I've given online on YouTube and longer presentations I've given from different trainings. So if you want to, you can find these slides on ResearchGate or other places if you just Google them. I'm going to upload these slides anyway after this. But essentially, there's two ways to install Solids4Foam. You can do it natively, which just means you download it from Git, as long as you have a version of OpenFOAM. So for the master branch, if you have foam extend 4.0, 4.1, ESIs 1812, 1912, or OpenFOAM 7, then the master branch will compile. Or the next release, which will be Solids4Foam 2.0 when it's released. But you can just use the next release branch now, compiles with these versions. So you just download it, and then there's an all wmake, run that, and it should just work. It should just compile. You can also download a Docker image. Yeah, so this, you just navigate into the folder, run all wmake, and then check the executable works. You can also use Docker. If you don't know what Docker is, it's like a lightweight virtual machine. So it's essentially just like a full computer in an image you download, and it has Ubuntu and everything set up already. So you just need to install Docker on your computer, and then you can launch a Docker terminal, and then it's all there. And if you use Docker, that's particularly convenient. If you don't bother learning it, I guess. Okay. Okay, example case. So I do lots of different example cases, and when I've done trainings in the past, so I always, each time I do a new training, I try to just update my slides just so I add to it in some way. So this one, since we're in Cambridge, I was trying to think of what could be cool to do with Cambridge. So Newton, obviously, this is his alma mater. So I found you can find a CAD of a bust of Newton online. So I downloaded it and meshed it with CF Mesh and added that as a tutorial. So we'll go through that now. So what is it? Yeah, so I just assume it's rubber, and I assume gravity is in this direction, and I just fix the bottom. So I just start off, there's no gravity, then gravity kicks in. So the whole thing is like fixed at the bottom, and imagine we were holding it sideways. It just kind of falls and bounces. So the material is elastic. So that means it doesn't dissipate energy in the mathematically perfect sense. So that should just keep bouncing back to position 0, down, back to position 0. So converting potential energy to elastic, storing it, converting back. So that should run forever. Numerical methods, the discretization may diffuse energy. It'll disappear or may explode if it adds energy or something like that. So for this, I'm using Foam Extend 4.1 and Solids4Foam on the next release branch. Some of the theory. So this equation here is conservation of linear momentum. It's basically mass by acceleration on the left per unit volume. So this is density. Displacement here. D is displacement here. So normally in solids, we don't solve for velocity. You can, but it's more convenient to solve for displacement normally. So the time derivative of displacement is velocity. The right-hand side, this is just divergence of stress, and this is gravity. So this is for an ideal, the most simple solid, which is an elastic solid. So this is actually pretty similar to like in Navier-Stokes. You'll have this term here and here in your Navier-Stokes formulations. And this would be viscosity, but it's what's known as shear modulus here. It's like the stiffness in shearing. This right-hand side term, normally you'd have grad P. So you'd have the gradient pressure. This is like a pressure term. It's just normally in solids, you calculate the pressure directly from the displacement or velocity field. You don't have it as an independent variable. And there's a variety of solution methods that are implemented in Solids4Foam, as are available in many finite element formulations. So you can do it implicitly, explicitly. If it's implicit, you can do it segregated or block coupled, or there's lots of things you can do. So maybe it's worthwhile just reviewing some of these concepts. So finite volume method, there's two things to note if I take a typical cell. The shaded area is your integration volume. That's what I'm going to call it. So we take the equation on the bottom, or any equation, partial differential equation, and we're going to try and force that on that piece of volume, that finite volume. Okay, that's what we're going to do. How do we do that? Well, we're going to write it in terms of some unknown, in this case displacement, but it could be velocity and pressure, and the velocity and pressure at particular points. So these points here, these cell centers, one way we can call those the computational stencil. Sometimes they call it a computational molecule. So to enforce the equations on that volume, that area, we're going to write this equation below in terms of the unknowns at those points there. So that's one stencil. You can have different formulations for different size stencils, but this is a typical cell-centered one. So that's the stencil and the control and the integration volume. For comparison, there's also vertex-centered finite volume methods. That's not the standard in OpenFOAM, even though I'll give a talk on that tomorrow if you were interested. So in vertex-centered, typically you define a volume around a vertex. So that's your volume that you're enforcing the equations on, and then you do in terms of the stencil of the points around it. There's some relative merits to doing that as well. For comparison, finite elements methods, they will enforce that equation on all the elements around a node. So not just split, they don't define a second mesh, they define it over all of those elements. So for that center node, they will enforce it over the volume of all of that red area in some weighted way. In contrast, the finite volume method enforces it just over the boundary, divergence terms over the boundary of its volumes. So that's like, not philosophical, that's an actual difference between the two methods. And just to note here, it's very subtle here, I should have made it a bit clearer. But if you look at a neighboring integration volume in the finite volume method, they don't overlap. Whereas a neighboring one in the finite element method, they actually overlap. So you doubly or triply or multiple times integrate over the same area in the finite element method. Whereas in finite volume, it's normally integrated once per area. Does that matter? Well, that's where the conservativeness tends to come from. So now you conserve what goes out of one goes exactly into the other. That's not the case in finite element. It's just on average balances things. One other distinction is if you look at the boundary of the mesh, cell-centered methods don't have unknowns on the boundary, whereas vertex centers do have unknowns on the boundary. That doesn't really matter normally, but in solid mechanics, you normally like to have unknowns on the boundary in terms of writing traction conditions. So that's one disadvantage of cell-centered, but you can add phase centers as unknowns as well. It's just tedious. And then just to mention implicit versus explicit, how you calculate your divergence of stress. If you calculate that in terms of an unknown displacement, you have to make a linear system, ax equals b, and solve all that. That's an implicit method. Or you can just use the old time values of d. That's an explicit method. But then you're subject to a current number of less than 1, so you need small time steps. So you can implement both of those. If you're interested, I would say if you want some bedtime reading, you can download this paper. I published this with my colleague Ismet Demirzic last year. So it's we have 600 references on finite volume methods for solid mechanics. So if you are interested in learning more about this, you can check out that paper. Okay, let's look at a case. So wobbly Newton. So if you download it, you can find this wobbly Newton case under solids linear elasticity. So what does the case look like first? So in this case, I'm giving an example of a vertex-centered finite volume method. That's implicit. So it solves for point D, which is the displacement at the points in the mesh. Okay. So you would expect in 0, there's point D. That's where your initial and boundary conditions would be specified. There's only 2 boundaries, 2 patches. There's the bottom. I think I call it base, and then there's the rest of it. I think I'll call it just Newton. So Newton is just like air. So that's just like 0 force. There's no force on them. It's like an interface. So there's a boundary condition called point solid traction. So traction is force per unit area. So you specified a 0 traction condition. On the base, I just set the value of point D. So we're in the point D file. So the value of point D will be 0. So there's no displacement. It just doesn't move. All the tutorials in Solids4Foam have an all run and all clean script. So if you go /all run, it will run the tutorial. In this case, if you open it up, it has a few commands. So it has Cartesian mesh, which is CF mesh. It's like snappy hex mesh. It's just a slightly different approach. So it's a Cartesian-based mesher. That makes the mesh. The way I defined the patches here was just I have a separate SDL. This is just the base, and I use surface to patch, which just makes a patch where that SDL is, just for convenience. That doesn't have an override option, so I have to move the mesh manually. That's what these steps are, just with the new patch. Then I run Solids4Foam. If I just look at the consonant system, so the only distinction between a normal OpenFOAM case and Solids4Foam is the first thing it looks for is a physics property dictionary. So physics property here. So physics property, it's a dictionary that only has, it just tells it, is this a solid or a fluid or an FSI case? That's it. So you just say solid fluid or fluid solid interaction. If you say solid, then it will look for solid properties. If you say fluid, it'll look for fluid properties. If you say fluid solid interaction, it'll look for FSI properties. And in that dictionary, you'll tell it about what type of solid it's going to solve. And then once you pick that, then it's essentially picking what solver is called, is the idea. So in this case, there's a variety of solid models, all solving the same equations, just different ways, implicit, explicit, or some different discretization approach. So we're using one called vertex-centered linear geometry. Just to comment on, maybe you're solids people and you don't need to know this, but most of you are mostly from a fluids background. So in solids, let's say an analogy for compressible versus incompressible in fluids. So in fluids, there's incompressible, compressible, where they're quite different like approaches to solving a problem. You might just say, well, if everything's compressible, just use a compressible approach. But then you're like, well, that won't be efficient for an incompressible problem. So in solids, there's something called geometrically nonlinear and geometrically linear. So all problems are geometrically nonlinear. And what does that mean? It means our equation, we're integrating over a volume, wobbly Newton. So when I apply force, he moves, his little eye moves a little bit. And the area of that little piece of infinitesimal piece of surface will change. So that means if we're integrating over that surface, it's unknown. So we're integrating over a mesh that we don't know yet. So that means solids are always inherently nonlinear because that's a function of displacement, and your stress is a function of displacement. You multiply them together. However, the standard approach is just ignore the fact the mesh is a function of displacement. And that's called a geometrically linear approach. That's an assumption. And that's also known as small strain approach. So if you open up SolidWorks to do a stress analysis, they make that assumption. So that's fine if thing's steel and it doesn't move that much or something like that. Not for rubber, typically. And then there's geometrically linear, where you actually have a nonlinear solution procedure which accounts for that. And in this case, it's an implicit discretization. Instead of the turbulence properties, we're going to specify the mechanical properties. In this case, a linear elastic. So linear elastic is like the most simple ideal elastic material. You specify something called E, which is the Young's modulus. It's like, if you imagine the material as a spring, it's the stiffness of the spring. And nu, which is the Poisson's ratio. So that's, if you have a spring, when you pull it, solids like to kind of preserve their volume to some degree, so they'll contract in the other directions. So when I pull it this way, it'll contract. 0.3 means if I pull by 1 in this direction, it'll contract by 0.3 in the other directions. So there are two constants to describe linear elasticity. And then we have density as well. And then we have G, which is our gravity, and applied in the y direction. Okay, let me try this. Okay, so is that okay? At the back, you can read the text. Okay. So Solids4Foam, this is inside the directory. If I ls this, oh, do I have the tree command? No, I don't. So this is the high-level format of Solids4Foam. So it follows the OpenFOAM design of the toolbox. So you have an application folder, you have an SRC folder with the libraries, and you have 2 tutorials, and then some other bits and pieces like third party. So if I go into applications, solvers, there's only one solver called Solids4Foam. If I go inside that, open up Solids4Foam, we can see we've included FE, CFD like normal. We've included something called a physics model. If I zoom down, there's no create fields. I just make something called a physics model. So this is a type of runtime selection. So when you run the case, this decides which class it needs to create. And so I make something called physics. I have an object called physics, and I go through the time loop. The physics object may want to set the time step. I let it do that. And then there's an evolve function, which is just solve whatever equations you want to solve, whether you're a solid problem or FSI or fluid problem. There's this to tell it it's the end of a time step, and then it may want to write some fields. So that's it. There's basically no real code in the solver. Okay, so if I go tutorials, inside tutorials, there's 3 folders: fluids, solids, and fluid-solid interaction. It's not my goal to reproduce all the fluids in OpenFOAM. That would be silly. So it's just the minimal fluids just to show a fluid works on its own, but that's not the purpose of Solids4Foam. So in the next release, there's just pimple foam, not icofoam, piezofoam, simple foam, because they're all a subset of pimple foam. You can get the behavior of icofoam, piezofoam, and simple foam if you just choose your settings for piezofoam, the correctors correctly. So it goes inside solids. Inside solids, the cases are broke down into different types of phenomenon or physics. The blue is probably not great there, sorry. So we have different types of material behavior. So we're going to go into linear elasticity. There's a few cases here. So wobbly Newton is down the bottom. I think I ran it just with some results to store it. So if I go all run, it'll run Cartesian mesh and then surface to patch, and then it starts running Solids4Foam. In this case, this solid vertex solver is using PET-C, which is a linear solver. So it's not using the OpenFOAM linear solver, it's using a different one. So you can see it goes through the time steps. It's taking like 5 or 6 seconds per time step, writing out some things about the stress, some other things like that as well. This is a transient problem. So if I open up FV schemes, we have a second time derivative. We don't have that in fluids. So you can have a steady state discretization, or you can have Euler, which is first order, or backward, which is second order, or in this case, it's using a Newmark beta, which is a type of second order popular in solid mechanics, I guess. You don't have any divergence scheme. You have no advection term. There's no convection or advection, so that's because it's Lagrangian. So it's just like the gradient scheme is the key thing, essentially. So if I find this case, not that one, the Newton run. Okay, so open up the case. So in this case, I've just so the tutorial runs quickly, I have a relatively low resolution version. So is and it's fine, but you can set the mesh density to be higher if you want to see what he looks like. So his nose gets a bit smoothed. Okay, so I have the results in this case. Here's one I prepared earlier. So for solids, if I play it, first thing you notice is, oh, it's not moving. So in this case, it's a small strain approach. So this is conceptually, people find this difficult to understand. We're assuming the mesh doesn't move and we're solving for the deformation on an on-moving mesh. So if you want to see the motion, you have to use a filter. So there's warp by vector. So I'm going to say move the mesh by the displacement field to show me what the actual deformation looks like. So then you can see him nodding along. So what does it print out? So you'll have a displacement field. So you can see the tip of his head is going to displace the most. We're saying it's 0 at the bottom. So his head displaces the most. I think this is set up for 3 periods. About the period of the wave is about 0.12, I think. So he bounces about 3 times here. What else gets printed out? Well, you have a stress tensor with all the components, but that's not that interesting to look at all the components. So normally if you're designing something, maybe not a bust, but you look at what's known as the von Mises stress, or it's also called the equivalent stress or the von Mises stress. So it's essentially a scalar stress which defines how likely a material is to fail. So normally if you're designing something apart in SolidWorks or something like that, you will look at the von Mises stress or the maximum principal stress. So normally if that gets to what's known as the yield stress of the material, that's the point at which it starts to break. So it's a scalar measure of how close it is to breaking normally. Von Mises is normally for ductile materials. So you can see here, if we look at that, oh, I need to rescale it, the peak of the wave. Oh, get out of the way, please. Okay. Okay, there we go. So in this case, you'll see you get a stress concentration. Let me rescale it again. Just down at the bottom corner. So it's where it's fixed. You get some stress concentrations down there. And then just under his chin, you get a little stress concentration. So if this is going to crack, in this mode, it would probably crack under his chin or where it's fixed at the bottom. You can also look at strain, which is a measure of like the deformation, where the material is being stretched the most. You can also run the case. I think I ran it here. If you go into mechanical properties, you can change it to an elastoplastic, so Mies plastic, a type of plasticity. You can change it to that. So in that case, I'm going to say when this von Mises stress gets to a value of, I think it was 1e⁴, I say that's the max stress it can withstand. Then it's going to start permanently deforming. So if I look at that case in comparison, if we look at the stress, so the stress can't go above whatever the maximum is. So I think it's 1e⁴. So in this case, this is elastoplastic. So when he bends back the first time, it kind of permanently deforms. So it dissipates energy. So then it'll just, whatever remaining elastic energy, it'll just bounce around that point. Okay, since we started late, I shall keep going. Okay, question in the chat. Yeah, so the question, oh, you can't see it. So the question is the point D displacement field solved for the displacements of the points directly, just like in dynamic mesh, or is it solved for the cell centers and then interpolated? For this particular solid model, it actually solves at the points. There's no interpolation. But there are ones that solve the cell centers and then interpolate to get a point D field. In this case, this vertex-centered one really is solved at the points. Okay, now to do an example of an FSI case. How do I hide this thing? This one? Okay, we're leaving it there. So this case is the dam break case. We just have a flexible dam. So we just kind of have a little piece of rubber dam. Okay, so the equations in the fluid, we have your Navier-Stokes equations, incompressible fluid, and we have this alpha equation. So solving for the phases, it's a multi-phase equation, so air and water. So that's what the fluid solves. The solid is as before, but we have an extra set of equations. So for a fluid solid problem, we have kinematic and kinetic conditions. So basically the this velocity at the interface of the fluid has to be equal to the solid. They can't be separate because then you'll get a hole which has nothing in it. Also, the kinetic ones basically say the force or traction at any point has to be equal and opposite. That's the idea. So that's what the coupling algorithm has to enforce. So I said there's two approaches, partitioned and monolithic. OpenFOAM uses, or Solids4Foam uses partitioned. Just a note on parallelization. The fluid gets decomposed into how many processes you have, and then the solid does, because they take turns. So if you have 8 cores, it'll be 8 on the fluid and 8 in the solid. That might not be the most efficient if you have a small solid and a big fluid, but that's the way it works. And the interface is stored on all cores as well, just to facilitate the algorithm implementation. So the only difference then in this case between what we saw previously is now we have 2 regions. We have a fluid and a solid. So like before, we physics properties, in this case, it's fluid-solid interaction. When it finds that, it'll expect to find a fluid and solid subdirectory inside 0, inside constant, and inside system. So if you want to specify your fluid boundary conditions, they will be inside 0 fluid, and then you'll have velocity pressure. If you want to specify the solid, it'll be inside 0 solid, point D, like before. So it's just like 2 cases in one, and they're stored in subregions, is how it works. This is like conjugate heat transfer. If you ever do that, that's the way they define this case setup. There's FSI properties, which have details about the coupling algorithm that are used. In the next release as well, there's Precise is an external software for coupling. So you've got the Precise adapter working with Solids4Foam. So I will add an example where it's Solids4Foam for the solid and then a conventional OpenFOAM solver for the fluid. It's not using the FSI coupling of Solids4Foam. It's just Solids4Foam solid and then a black box to this external Precise coupler. Just in case you're interested. So Precise is a dedicated coupling software. So in this case, we have our like interfoam boundary conditions for the fluid and properties for interfoam. And then the solid, like before, we have mechanical properties. The only thing to be aware of, it's not interfoam, it's interdiem foam, because the fluid mesh will move. They all have to be ALE formulations. They all have to be dynamic mesh formulations for fluid-solid interaction. Okay, the all run in this case will run block mesh on the solid, on the fluid, set the fields in the fluid. So that's the initial alpha field, and then run the solver. So if I try that out, so I'm going to go back, fluid solid interaction, flexible dam break. This thing is annoying the hell out of me. Run all run. So that is running the case. If I just stop it and run Solids4Foam, you'll see the solver running, printing out time steps. Let me see. I have the results here. So when I open this, if you're not familiar with multi-region cases, in ParaView, it will see a fluid mesh and a solid mesh. So you could load each one individually. But there's a convenient filter in ParaView called extract blocks. So if I select on this here and I go search, extract, or extract block. So extract block lets you say, I want to take the fluid. So I'm going to call this fluid. Then I select the original one again, go filters, recent, extract block, solid. Why am I doing this? It just means I can visualize or display different fields in the solid versus in the fluid. So once again, the solid is a non-moving solid. This is a small strain one. So if I play this, if I turn off the solid for a second, and I look at the alpha field in the fluid, you'll see, I set this to 2D, you'll see the fluid mesh updates. But if I actually look at the solid isn't actually moving at all, because it's calculating the deformation, and that deformation is passed to the fluid, so the fluid updates, but it's doing its integral over a non-moving mesh. So it's doing the calculations on a non-moving mesh. So if you want to actually see the movement, you have to use the warp by vector. You can also see it's a non-conformal mesh. So there's different ways to map. It's using GGI or AMI to do the mapping in between, so the interpolation. So if I warp the vector by point D, and this point D is actually interpolated from D. So this is not solved for. This is actually a cell-centered formulation. And let's look at the displacement of the solid. So then if you visualize that, then you'll see it aligns as expected. Okay, and then if you wanted to look at things like the von Mises stress, you'll see it's high at the front and at the back of where it's fixed. Where it's most constrained, that's where you get the highest stress. So if it's going to break, it's going to break at the bottom. And that's classic for bending problems. You have, if you bend something, it'll crack from the outside, not from inside. So, I can see there's some questions in the chat. I'm going to wait just till I finish because I'm almost finished, and then I'll go through those. Yeah, just some comments on kind of future directions in Solids4Foam. I know this is a very short introduction. Well, maybe you felt it's very long, in which case apologies, but I think it's short. So some kind of future directions, efficiency and robustness. So Solids4Foam works on cases, but in some cases it's quite slow. In some cases, it's not very robust. By robust, I mean the case explodes or doesn't converge very well. And this is generally a comment on FSI procedures anyway. So efficiency, these new block coupled methods are probably one way to speed things up. And so that's where I'm focusing effort. And then robustness, monolithic methods may be more long-term, but also linking external couplers, precise, and other external couplers show better performance from benchmarks than the inbuilt coded ones. So they're the sort of directions that we're going. Very good. That is the end of my talk. I'll share all these slides. I'll probably just put them all up on ResearchGate. I don't know what they do with the recording. I'm happy for it to be put on YouTube, but I'll leave that to her for whatever they're going to do with it. So if you have any questions, feel free to ask me while you're thinking about it. I'll answer. There's one question here in the chat. So Anis asks, can you explain comparison in performance between vertex-centered and cell-centered? I'll try. So in terms of efficiency as in speed, in this case, the vertex-centered is block coupled. So if you compare block coupled cell-centered and vertex-centered, they're the same speed, give or take. If you have a segregated, which is the standard or the default approach, generally that'll be slower. And in some cases, very thin structures, it'll be much slower, as in it could be 100 times slower. But that's block coupled. So that's a coupled solver versus a non-coupled solver. So that's not really vertex-centered versus cell-centered. In terms of accuracy, they're pretty much the same. I'm going to give a talk tomorrow, and you'll see that the accuracy is pretty similar. It just depends on the actual discretization. There are some convenient things. So for multi-material cases, if you have a piece of aluminium stuck to a piece of steel, then you get a discontinuity in the gradient of your solution field. So if you have a vertex-centered method, you have a point right on the interface. So you don't have to do anything special. You add a contribution from the left and the right, and then that's it. In cell-centered, you have a jump like in multi-phase, so you have to like do something special with the gradients. So there's some conveniences in that regard. The inconvenient thing is everything in OpenFOAM is written for cell-centered, so you have to rewrite everything yourself if you want to get a gradient. Another question online, a really stupid question: would it work if I change the solid to a fluid with an infinite viscosity and positive spring constant? Yeah, there's definitely ways to do it. I'm involved in a number of projects for additive manufacturing and to do a laser-based fusion, and then you have a solid and a fluid, and then the fluid melts and turns into, or then solidifies and turns into a solid. In that case, the standard thing to do is model the solid as a very viscous fluid. So it depends on what your goal is. Infinity won't work in anything numerical, but yeah, I understand a very big value. Another one, I'm new to Solids4Foam. Is it possible to use OpenFOAM and Waves2Foam? Yeah, the master branch works with Waves2Foam. I haven't tried it recently, but yeah, it does work with Waves2Foam. There's a guy who was in UCL, Lu Fang. He's in Loughborough now, I think, and he's done a lot of stuff on modeling ice and stuff using Waves2Foam and Solids4Foam. Another question, for solid models, we have two options, nonlinear and UNS nonlinear. where uns is the class name, unstructured. Yeah, so in solid models and Solids4Foam, some of them have a prefix name that starts with uns, uns. It's a different discretization of the gradient at the face. So this comes from Jako Jukovic. He came up with some methods where if you want to calculate the gradient at the face, there's a couple of ways to do that. One way is you calculate the cell center gradients and interpolate it. Another way is you directly at the face calculate the gradient using the surrounding values in some way, or maybe just do the normal part by neighbor versus owner and then interpolate the rest of the gradient. So there's uns methods which have shown to be more accurate, particularly on unstructured meshes, but no, all of them can be used for unstructured meshes. It's just maybe uns should be just called more accurate discretization, but it's more expensive, it's slower. Okay, that's the online questions. Anyone have any questions in the room? Yeah, sure. No fundamental difference. So the question for people online is, what's the fundamental difference between the approach Precise adopts and the approach that Solids4Foam adopts? So they're the same. So in fact, we claim to implement the same algorithm, but theirs tends to perform better. So strongly coupled, loosely coupled, people have different words for what they mean by that. Typically, what they mean, I think, is strongly coupled means you go to a time step, solve fluid, solid, fluid, solid, and you keep going till they converge to some tolerance. I'm not sure. I'm not sure. I know I've run cases and it's essentially the same thing. So that's their strong coupling. So it's the same idea. There are some subtle differences, no doubt, in the implementation. From benchmarks, it seems that some of their implementations show better convergence that I've seen. So that's one reason I want to include the adapter, so you have the option to use that. There's another question just behind you. Thanks, Shannon. Sure. So there are some explicit solvers in Solids4Foam, but I would say they're more demonstrators, proof of concepts, than a code that will work in most cases. So I have set it up. This wobbly case will work. It's super slow because the time step is like 1 × 12 or something, but it will work. But people who are focused on fast dynamics, there's a group that are originated in Swansea, and so Antonio Gil, Javier Bonnet, a few other guys like that. And they're using OpenFOAM as well now. There's a guy, Gibram Haider, I think he comes along to these sometimes. So they are implementing fully explicit Riemann solver finite volume solid mechanics methods for large strains. So they do like very similar to compressible flow. You have these Riemann solvers where you assume it's kind of like a different flavor of finite volume cell centered. You assume there's a discontinuity at every face, and then you resolve that as it propagates around. So yeah, that's for fast dynamics, that's fine. Explicit solvers, if it's not a quick problem, they're slow. I mean, if it's longer than 1 second, you're going to have to do a billion time steps to do it. But they're robust. So if you're BMW, you do a car crash simulation, finite element, it's going to be explicit because it works. So that's not a focus that I've focused on in Solids4Foam. There are examples that will work, but yeah, there are those codes that they've publicly shared, some of them from Swansea in OpenFOAM. They're really focusing on that. Yeah, thanks. With compressible flow? Not really. I mean, you can do it. The missing piece is like the temperature equation. I haven't set up coupling for that. So that's maybe another reason for Precise. Then you can have your coupling of that as well. So if you need the temperature equation, that isn't in the interface at the moment. But there are solids with solve for temperature. So then as long as you have a coupler that allows for that. So there is, for FSI cases, for incompressible cases, sometimes it's nice to have a little bit of compressibility because it helps convergence. So like in arteries or something. So there's like these weakly compressible solvers, like I guess, not like sonic foam, I guess, is kind of weakly compressible. So there is weakly compressible ones, but they're basically incompressible. It's just it improves convergence for FSI cases with a bit of compressibility. Yeah. No, there's no reason you can't do it. It's just, it depends. I guess if it's like row central foam, then I guess you need the temperature field or enthalpy field or something. You can't ignore that unless you have a really well insulated solid. Well, maybe you can, but yeah, no, the overall general approach will work. Yeah, sure. Yep. Yep. This is partitioned. So solve solid, solve fluid are independent, and you just exchange information. Monolithic, essentially one solver and you have one matrix, and the discretization has to be it's more challenging to implement. I mean, it has actually been demonstrated in OpenFOAM. There's a Greenshields Vankovich paper from '99. There's one in 2004. They demonstrated it. I have some version of that code. Doesn't work very well. So not that it won't work very well. They were using a segregated algorithm. You get pressure jumps at the interface. They didn't sort all of that stuff out. So it can work. It will work. It's just takes some projects and people take some painful PhD years to get it working well. FSI and Phoenix. So I've done a tutorial in Phoenix, and then I forgot how to use it and haven't used it since. But Phoenix, does that have? I know it does solids, but does that do FSI in Phoenix itself? And is it a monolithic or partition? Do you know? I don't know. Okay. Yep. Sure. So ComSol is it's finite element anyway. That's one distinction. So that's fine. It works for fluids. There are some differences in fluid mechanics in finite element, obviously. Some messing around with convection terms and stuff. So that's fine. So no, it's fundamentally the same thing. Monolithic. That's monolithic's independent of finite element. So I don't know the details of their solver. Maybe you've experience with it. You can say if it's good or not. You're okay. I don't know then. Yeah, you try it out and come back in 2 years and tell us if it's good or bad. Then. Yeah, no problem. Any other questions? Yep. So for most of the solids in Solids4Foam are implicit. So that means they're unconditionally stable. So they're independent of the current number in terms of stability. Some material models will be time dependent, like plasticity. So then there is an accuracy. If you don't have a small time step, then it's less accurate. So there isn't a condition on them. The explicit solvers will. You have a current number. You need to keep the current number less than 1, or probably less than like 0.5 or something like that. In terms of FSI, though, one thing people like to have is a different time step for the solid and the fluid. That's not implemented, so that's a bit annoying. So I think Precise can do that. I'm not sure. I think Precise lets you have different time steps, but not in Solids4Foam at the moment. If that answers your question. Sorry, I forgot. I'm not repeating the questions for online people anymore. Apologies. Any other questions? Yep, please. So for a multi-phase, like if you've interfoam, then they're independent because it's partitioned. It's just an interfoam case and a solid case. So any boundary condition you can use in interfoam, you can use in like interfluid in Solids4Foam. So I'm not so familiar with them, but there's like a constant angle one and something else. So you can use all of those. And it's just the only thing you need is the force. So the interface just needs the force, which is just like pressure plus viscous stress or whatever. So the alpha equation, it doesn't really matter. So this is not my area, but I think the Neumann triangle is like when you have like two solids and then a fluid, is it, or what is it? It's like yeah. No, I mean, as long as the boundary condition on the solid is or the boundary condition on the fluid on the interface, like from the fluid side, as long as the boundary condition is correct for the surface tension or whatever, then that can be captured. Yeah, it should work. Like that's independent of the solid. The only thing the fluid needs from the solid is its geometry. So it gets that, and that just comes by the mesh. So you can do whatever you want with boundary conditions, give or take, except for force. That's the main force. Well, I'm not sure if I'm answering your question. I probably not understanding it fully, but we can chat afterwards if that helps. Any other questions? I'm going to be around for the rest of until Thursday anyway, so we can always chat more. I guess people want to go get a coffee. Okay, cool. Yeah, okay. There should be ones, there's like beam and, well, what do you mean moving? Oh, I understand, Probably not, but yeah, let's chat about it. And then you can tell me what you want and I'll tell you how difficult it's set it up there. Okay, thanks so much.